The next topic is dilations of lines. So the first thing here is on the coordinate plane, if you're given a line, remember there's two rules you have to know. So if the center of dilation is on the line, you'll get out the same line. But if the center of dilation is not on the original line, you're going to get out a line that's parallel. So for this one, let's go ahead and start by just graphing my old line and the center of dilation. So the center is negative 4, 3, and my old line is y equals 2x plus 1. So that means I'm going to start at 1, and I'm going to rise 2, and then right 1. So up 2, right 1, up 2, right 1, then backtrack. So then I can go ahead and connect. So here's the original. So we should label that because we're going to be dealing with another line. We want to make sure that we can determine which line is which. So y equals 2x plus 1. The center of dilation is over at negative 4, 3. So 1, 2, 3, 4, up 1, 2, 3. So there's the center. So since the center of dilation is not on the original line, that tells me my new line will be parallel. So let's just make a note of that. So new line is parallel to y equals 2x plus 1 because the center of dilation is not on the line. So also keep in mind that you can't just multiply the y-intercept by whatever the scale factor is because the center of dilation is not at the origin. So the center of dilation here is at negative 4, 3, which means we're actually going to have to do this whole thing graphically. So the one thing I do know is that my new line is going to be parallel, so it's going to have the same slope. So when I write my equation here, I'm going to use this slope, but I'm not going to use the y-intercept. So the new line is going to have y equals 2x, and then I have to find the rest of it. So what I'm going to do to find the rest of it is I'm going to use my scale factor. So the scale factor is 1/2, and this is what I'm going to find the y-intercept, I'm going to have to multiply by 1/2, which really means I'm going to take half of the distances from the center to the y-intercept. So meaning I'm going to start at the center, and I usually just go to the y-intercept, but really you could go to any point. So I'm going to go to the y-intercept just to be consistent. And I start at the center. I had to go down 1, 2, and then over 1, 2, 3, 4. So I went down 2, right 4. I need to take half of that, and that tells me that the new line will actually get closer to the center because my scale factor was less than 1. If the scale factor was, let's say, 3, then the distance is going to be 3 times away from the center. So in this case, it's going to get half as far. So instead of going down 2 over 4, I'm going to go down 1 over 2. So there's my new point. So this point my line has to pass through. So I'm going to just make a note of that. So the new point is negative 2, 2. So that's the point that my line has to pass through, and it has to have a slope of up 2 over 1, or positive 2. So there's two ways you can algebraically solve this. You can plug into y equals mx plus b, plug in your slope, which we know it has to be 2, and plug in this point for x and y. So it would be 2 equals the slope, which is 2, times the x value. So you get 2 equals negative 4 plus b. Add 4 to both sides. So you get 6 equals b. So I know that this has to be 6. So that's my answer, but you could have also done this graphically. So meaning I could start at this point. It becomes one of those problems that you've seen before where you have to write an equation that's parallel to this line passing through this point. So starting at this point, you go up 2 over 1, up 2 over 1, until you get the y-intercept, which you'll see the y-intercept is 6. So from here, if I want to just finish it out and graph it, and then we'll be all set. So there's my new line. It's closer to the center, which makes sense because the scale factor was less than 1. So that's why. And I'm going to put just arrows on here, label it, and that's it. So remember that the slope will stay the same as long as the center of dilation is not on the line. And the y-intercept, I did not multiply that y-intercept because remember it was 1. I didn't just multiply it by the scale factor. That only works if the center is at the origin. So if the center were at the origin, then I could have just done 1 times 1/2 and got the y-intercept. In this case, you can see that's not even close to being the right answer. So then the next one here is looking at segments, so very similar, but just answering some multiple choice questions. So AB, shown at the right, is dilated with a dilation centered at the origin. So here's my center. And then it says with a scale factor of 5/2. Which of the following statements regarding AB is not true? So it's talking about A prime, B prime. So I say we actually do the dilation. So what you would do is you would count from A to each point. This time you actually have to count to each point because it's a segment, so you want to graph both endpoints. You don't want it to just go on forever. Where a line, you really just have to get one point and then just use the slope to continue it, and it continues forever, so you just put arrows on. But if you have a line segment or a triangle or a rectangle and you're trying to dilate it, you have to dilate each individual point. So that's why I have this one on here as well. So I'm going to count from the center. I had to go over 2, up 1. So I went over 2 and then up 1, but I need to multiply those distances by 5/2. So if you multiply those by 5/2, that really means you're going to have to travel. So 2 times 5/2 is going to be 5, and then 1 times 5/2 is going to be 5/2, which is 2.5. So this is really what you're going to travel. So you're going to travel from the center over 5, so 1, 2, 3, 4, 5, and then up 2.5, so you're just going to have to approximate where that goes. And then if you do B, so from the center it's over 2, up 1, so it's the same distances, so it's going to be over 5, and then up 2.5 again. So these are the primes. So if I connect those, there's my new picture. So now if we look at the questions here, AB will be parallel to A prime, B prime. Yes, that's always going to be true because dilations preserve parallelism, meaning they'll always stay the same, the slopes of the lines. The next one here, AB is equal to 5/2 times A prime, B prime. So what that means is that AB, the length of AB, is 2.5 times the length of A prime, B prime. That's actually backwards. That's the opposite of what is true. A prime, B prime is actually 2.5 times AB. So this one is not true. If we look at the other ones here, A prime, B prime is an enlargement. Yes, that's true because our scale factor was bigger than 1, and the coordinates of A prime will be, and we already checked that out, -5, 2.5. So that's all good. So the next topic here is similarity. So whenever you see pictures where you have these small triangles inside of larger triangles, always look to see if the triangles are similar, because if they are, then you can set up a proportion. That's how you can solve these. So for this one, since I have these parallel lines, that automatically means that these triangles are similar because one, we have reflexive property, but then also we have these corresponding angles that are congruent. So then that makes the small triangle similar to the big triangle. So we can set up a proportion of small triangle to big triangle. So if I take 12 and I put that over the entire side, which is 27, and then I take x and I put that over the entire side, and then we can just cross multiply this and solve it. So we get 27x equals 12. Make sure this goes in parentheses, x plus 8.75. And then we're going to distribute this. So we have 27x equals 12x plus 105. Subtract 12x from both sides. So you end up with 15x equals 105. Divide by 15, you get x equals 7. And then for this question, it just says find x, so we don't have to plug in or anything. That's it. So it's just basically you have to be able to identify that these triangles are similar. If I look at the next one here, these lines aren't parallel, but I have congruent right angles, and then I also have that reflexive property. So again, I can do small triangle to big triangle. So we're trying to find x, which is on this bottom side here, which means I need to find this piece right here so that I can do, because that's what corresponds to x. So the first thing you have here is, you notice that you have a right triangle. So this is actually a 3, 4, 5 right triangle, but you could also just do 3 squared plus y squared equals 5 squared, and you would get that y equals 4 when you solve that. So that means that this is 4. So you have to know that before you can set up your proportion, or just recognize it as it's a 3, 4, 5 right triangle. So now I can say 4 to x equals 3 to the big side, which is 6. So notice I don't use 5 for the proportion, but you needed the 5 so that you could find the bottom, because you have to make sure you use the pieces that correspond. So now I can just cross multiply this, so I get 3x equals 24, so x equals 8. Next example, again, continued with the similar triangles. Look to see if they're similar. Well, in this case, yes, again, they are similar because you have the reflexive property and they already marked the congruent corresponding angles. So again, you're going to do small triangle to big triangle. So 6 corresponds to this entire side, which is 6 plus x. And that equals 9, which corresponds to the big triangle's bottom, which is 15. Cross multiply, make sure this goes in parentheses. So I have 9 times 6 plus x equals 90. Distribute that. So you get 54 plus 9x equals 90. Subtract 54 from both sides, so you get 36. Divide, and you get x equals 4. And then the last one is a situation where, again, you have two triangles, but it's not a small triangle to a big triangle. It's two triangles, and they have parallel marked. So as soon as you see the parallel, you should be looking for the Z shape. So you have these alternate interior angles. I'm just going to erase that so it doesn't look crowded. So we have alternate interior angles. You also have vertical angles. So by angle, these triangles are similar because you have parallel lines imply congruent alternate interior angles and then vertical angles. So that means triangle 1 is similar to triangle 2. So when I set this up, I'm going to set it up so that I compare triangle 1 to triangle 2. So if I look at x, that's what I'm trying to find. 5.2 corresponds to that x. And then be careful with this one because it's twisted, or look at the angles that are congruent. So angle E and angle A are congruent, so that means these sides are the corresponding sides, and then D and B would be congruent, so that means 6 corresponds to 3. So 5.2 to x equals 3 to 6. And then cross multiply, so you get 3x equals 31.2, x equals 10.4. And then from there, the next topic is right triangle trig. So right triangle trig is whenever you have a right triangle and you have an angle involved. So you have a couple missing sides and you have an angle that's involved. If it was just 2 missing sides and you're trying to find the third side, well then that means that you would be doing Pythagorean theorem. So for this one, we want to find x to the nearest degree. So x is my angle, so I'm going to go ahead and label these. So this is the opposite, this is the adjacent, and the hypotenuse I have nothing on, so I'm not going to use the hypotenuse. So you think about SOHCAHTOA, you're using O and A, you're not using H, so you cross off anything with an H. So it means I'm going to be using tan, so it's going to be tan of the angle, so tan of x, equals the opposite, which is 15, over the adjacent, which is 20. Now you're trying to get x by itself, so this is where you're going to take tan inverse of both sides so that you can cancel out the tan. So it's going to be x equals tan inverse of 15 over 20. and we're trying to find x to the nearest degree, so you end up with 36.869897645, so on. But we want to the nearest degree, so it's going to be 37 degrees. And it just says find x, so that's it. The next problem here, you have this shop and you're trying to find, so they give you all this stuff, angle of elevation. Remember, that's coming up from the ground. Angle of depression is, if you were at this point, you draw a horizontal line, and then that angle down is the angle of depression. Remember, angle of elevation, angle of depression are always equal to each other because they form the Z shape, the alternate interior angles. So it gives you all these measurements, and it says that how tall is the sign. So basically what you're trying to do is you're trying to find this distance right here. So find this height. So that means, if you look, you can see that I have two right triangles. I can't just use this triangle right here because it's not a right triangle, so I can't use SOHCAHTOA on that. So instead, what you're going to do is you're going to use the smaller right triangle. You're going to find that side, which will be x, and then I'll use the bigger right triangle because I have an angle and I have a base for it. I'll find that entire thing, which we'll call y, and then what we'll do is we'll just take y and subtract off x, and that'll give us what we're looking for, which is this distance right here. So step one, let's start with the finding x, the small triangle. So find x. So 31 is the angle here. So this is going to be our opposite. If you go across from it, this will be the adjacent. Hypotenuse you're not going to use. So that means you're going to be using tan. So it's going to be tan of 31 degrees equals opposite over adjacent. Put this over 1, cross multiply. So you get x equals 14.4207. And remember, I'm going to be using that exact answer. I don't want to round till the end. Then the second step, I'm going to find y. So it means I'm going to be using the big triangle. So I'll be using the 42. And then, so it's going to be, again, opposite over adjacent. So this is the opposite. So it's going to be tan of 42 equals opposite, which is y, over the adjacent, which is 24. So put that over 1, cross multiply. You get 21.6097. And again, I'll use that exact answer. So then that means the last step to find the height of the sign, you're going to take the 21, which is the whole thing, and the 14 and subtract it. So I'm going to, the height of the sign, so 21.6097, and remember you're using these exact answers, minus 14.4207, so I'm arrowing up in the calculator, taking those exact answers, and I'm getting 7.189. So the question, if we go back up top here, says round to the nearest tenth. So that means 1 decimal place. So it would round up to 7.2. So 7.2, the units on this were feet. So there's your answer. So I'm just going to leave this as 7.2. This computer has a mind of its own right now. And there you go. So the next topic here is just going through quadrilateral properties. So for this, you're probably going to want to just pause the video because I actually have these filled in. So I just want to kind of quickly talk about how to do coordinate proofs, or even if it's a Euclidean proof, a statement reasons proof, when you have a different type of quadrilateral that you're trying to prove. Because remember, there's always one 6-point question is a proof, Oftentimes they'll give you some type of quadrilateral with triangles inside of it, and you're trying to prove that the triangles are congruent, but not always. Sometimes they might give you triangles inside of it, tell you it's a parallelogram, and then you have to prove it's a rhombus. So you should know the process for proving each of these. So the first one is a parallelogram. So if you're trying to prove that you have a parallelogram, there's different ways that you could do it. If you're on a graph, you could use the distance formula and show that both pairs of opposite sides are congruent. So you would be showing opposite sides are congruent. Even if it were not on a graph, you just have to show both pairs of opposite sides are congruent. You could also show that opposite sides are parallel, which would mean the same slope. So you'd be using slope formula if you were on a graph. Otherwise, maybe if it was a Euclidean proof, you could be using alternate interior angles to prove parallel lines if the alternate interior angles are congruent. The other one that's not as common but could be used is to show that the midpoints of the diagonals are the same by showing that the diagonals bisect each other. So that's another option. So those are your most common ways to show that you have a parallelogram. To show that you have a rectangle, you have to first show that it's a parallelogram. So think about the flow chart. It starts with a parallelogram, then it goes down to a rectangle. So since it passes through a parallelogram, you have to first show it's a parallelogram. Then you can show that it has one right angle, and to do that, you would use slope, or Euclidean proof some other way with perpendicular lines to prove that you have a right angle. Or you can use the distance formula. Once it's a parallelogram, you can use the distance formula and show that the diagonals are congruent. That would make it a rectangle, because that's the unique property for a rectangle. The other option too is if you don't want to prove it's a parallelogram first, you just show that it has four right angles, which means do the slope of all four sides, show that the sides next to each other are flipped and negated, and that would mean you have four right angles. For a rhombus, you can first show again that it's a parallelogram, because in order to get to a rhombus on that flow chart, you have to pass through parallelogram. So you show it's a parallelogram first, and then you can show that two consecutive sides, so two sides next to each other, are congruent. That would make it a rhombus. Or you can use slope and show that the diagonals are perpendicular, so it'll show that they're flipped and negated. That would be only if you show it's a parallelogram first. If you want to skip the parallelogram part and go right to proving it's a rhombus, just show all four sides are equal. So if you just show that all four sides are congruent, then you could show it's a rhombus without necessarily having to talk about it being a parallelogram first. And then the last one is if you have to prove a square. Well, to prove a square, you just do everything. So think about where the square is located on the flow chart. It's located on the bottom. So it means you had to pass through all of these other things. So you had to show it's a parallelogram, rectangle, and a rhombus, meaning it had to pass through all three of those. So that would be how you could show a square. Otherwise, you can just show that it has four right angles and four congruent sides, meaning it is basically taking these two things and putting them together. That would make it a square. So you could do that as well. So like I said, if you still need to copy this, just pause it and then unpause, and I'm going to continue. So for right triangles, another topic is sometimes when you have a picture like this where you have the big right triangle with the altitude drawn, this is a Papper-Hilp scenario. So as soon as you see this picture, you want to be thinking Papper-Hilp, because it's a large right triangle with the altitude drawn, creating two more right triangles. So for this one, it says find AC. So I'm going to put an X there. And then if you look at what you're given, the X is on the leg. So really, to determine if it's Papper-Hilp, what you do is you just look at the altitude, and if there's something there, or if you're trying to find that, then that means you're going to use PAP, because it stands for part over altitude equals altitude over part. But if there's nothing there and you're not trying to find it, you're not going to use PAP. So for this one, I'm not going to use PAP. I'm going to be using HILP instead. So that means it's going to be hypotenuse over leg equals leg over part. So the hypotenuse is this entire hypotenuse. It's the hypotenuse of the big right triangle. So this is actually going to be 15. So it's going to be 15 over the leg. So this is, again, the leg of the big right triangle. So these are all in relation to the big right triangle. So it's the hypotenuse of the big right triangle, the legs, and then the parts of the big right triangle, or the altitude of the big right triangle. So the leg is going to be the x equals leg. And remember, the part always has to make the smiley face, so it has to be the part next to the leg. So that means it's going to be over 12. Cross multiply that. So you end up with 180. And then we square root both sides. So we're going to have to break this down. So it's going to be x equals, so break 180 down. So 36 is the biggest perfect square that goes into 180. And then 5 is what's left over. So 36 times 5 gives me 180. So then this becomes 6 square root of 5. So the length of AC, which is what we're trying to find, is square root of 6 times the square root of 5. Now remember, if you can't get this radical, just type all these answers into your calculator. Type this into your calculator, square root of 180. See which one matches, which decimal matches, and that's going to be your answer. So keep that in mind. Otherwise, all you're doing is you're really taking the 180, you're just dividing it by your perfect squares until you get something that works. So like you divide it by 4, you divide it by 9, and if you can keep going bigger, so in this case, the biggest one that I could divide by was 36. So your perfect squares are just all your numbers squared. So 2 squared, 3 squared, 4 squared, 5 squared. 1 squared is kind of not really going to help you, so we don't really worry about that one. And then the last part here says find CB. So that means you're going to find this. So now what happens is you could do HILP again. If you wanted to, you could call this the next leg and do HILP again. But what I'm going to do is use Pythagorean theorem, only because I want to review that with you. So since I have two sides and I'm trying to find a third, I'll just call this y, we'll do Pythagorean theorem. So I'm going to have y squared plus, and notice it's 6 radical 5, that whole thing's going in parentheses, equals 15 squared. So y squared equals, now this you need to type in your calculator in parentheses, or you need to think of it as you're squaring each part. So you get 180 equals 225, and then subtract 180, so you get 45, and again, square root it, break it down. So you have square root of 45. Think about numbers that you can divide 45 by. So perfect squares, we have 1, 4, 9, 16, 25. Those are all our perfect squares. So 9 goes into 45 5 times. So 9 times 5 is 45, which means I have 3 radical 5. So then the answer would be CB, if you actually make sure you answer the question, is equal to 3 radical 5. So that would be this choice right here. All right, and then the last part here is just using rigid motions to verify that you have congruent figures, or to prove you have congruent figures. So for the first one here, which rigid motion will verify that ABC is congruent to triangle DEF? So we have to just figure out, how did I get from one triangle to the other? Remember, sometimes you can just see what happened, but if you can't and you're having a hard time figuring it out, look at the orientation. So go in whatever the order is here, so ABC. And then if I switch that and go DEF, now you can see that the arrows are going in the opposite direction, which means that the orientation changed. So that means that a reflection had to occur if the orientation is different. So you can see, if I were to flip triangle ABC onto triangle DEF over using a reflection over the x-axis, that would work because that distance is the same between each points. So to write this up, I would say triangle ABC is congruent to triangle DEF because a reflection over the x-axis will map triangle ABC onto triangle DEF, and reflections are rigid motions which preserve or keep congruent, which preserve um, angle measures and side lengths. So this verifies that the triangles are congruent. Make sure that when you state these types of proofs, so they're almost like a proof, you mention the fact that you have rigid motions, and you need to mention not just same shape and same size, but you need to mention that the angle measures stay the same and so do the side lengths. So if you don't say preserve, you could just say which create congruent angles and congruent sides, but you need to make sure that you mention sides and angles stay the same. If we look at the next example here, same idea. We're going to start that with P-A-R-T. So P-A-R-T. So I'm just going in whatever the order is of these letters. And then I'm going to go to this one. So H-G-F-E. Take a look at the direction. So opposite direction. So opposite orientation is what that's called. So we know that a reflection occurred. But there might not just be a reflection, because if I just reflected this down or I reflected it over, it's not going to map onto this. So we do know that a reflection occurred, but there's something more that happened. So let's start with, if I just flip this down over the x-axis, what'll happen is it'll end up being in this same position. So let's start with that so we can kind of see what it looks like. So if I go down 2, so there's T prime, R is 1, 2, 3, so 1, 2, 3. And then A is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 1, 2, 3. So there would be, if I did a reflection over the x-axis, see how now it's in the same position? And I would always start with that. Just do a reflection, and you can pick a different line if you want, because then what you can do is, if it's not in the same position, well, then it's easy to fix it by just doing a translation, because you can adjust your translation however you need to so that this figure actually maps onto the last one. So when I write this up, I went from shape 1 to quadrilateral 2 to quadrilateral 3. And then my translation to match these up is going to have to be T prime has to get to E. So it's going to have to be right 1, 2, 3, 4, 5, up 1. So translate right 5, up 1. And you should just check it for some other points too, make sure it works. So A prime would be 1, 2, 3, 4, 5, up 1. So it does work. So to write this up, I can say that quad P-A-R-T is congruent to quad H-G-F-E because a reflection over the x-axis followed by, so if you reflect over the x-axis followed by a translation right 5, up 1 will map quad P-A-R-T onto quad H-G-F-E. And then we'll say that basically what we said in the last one, reflections and translations are rigid motions which preserve angle measures and side lengths. So again, making sure that you state that those angle measures stay the same and side lengths stay the same is important. Also making sure that you say which direction you're going. I didn't mention that in the last example, but you need to say which shape are you starting with, because otherwise all of these are going to be backwards. So you have to say, okay, I'm mapping quad part onto quad HGFE, meaning I'm starting with this one and I'm ending with that shape. It doesn't really matter which one you start and end with, but you have to specify. Otherwise, you won't get full credit on that. You could even get 2 points off because it could be a conceptual mistake because you're totally not stating the right movement because you're going the wrong way. So make sure that that is stated. Make sure you're specific with these. So you're saying exactly what you're reflecting over and exactly what you're translating by. If there was a rotation, make sure you say the center of rotation and the angle of rotation. Dilation, center of dilation, the scale factor of the dilation. On dilations, remember, are similarity transformations though. So that would prove similar figures, not congruent figures. So then the last thing here is just more with properties of dilation. So these could be like multiple choice type questions. So I have A prime, B prime, C prime is the image of ABC after a dilation centered at A using a scale factor of 4. So let's just start with drawing this out. So I'm just going to pick a triangle here, A, B, C. And if I dilate this triangle centered at A with a scale factor of 4, you could actually do this using a compass. So what you would do is you would measure this distance and then you would do 3 more of those. So I'm just going to kind of make it look like it's 3 more of them. So 1, 2, 3, and then 4. That's where B prime would go. And then C prime, you would measure that and you would go 1, then you would go 3 more. That would be C prime. And when you connected it, this triangle would be 4 times the size of the original. So I basically just went 3 more distances away, so it was 4 total from the center. So A prime would stay in place. So to figure out this, the blanks here, AB, so if I compare AB, the relationship to A prime, B prime is going to be it's 1/4 the size, because that's smaller. BC times 4 would get me the large B prime, C prime. If you divided the ratio between the sides, AC to A prime, C prime, this is a 1:4 ratio, so 1:4. The angles will always be equal, so no matter what, angles are going to be equal to each other. There should never be a ratio between them. Notice I put equals when I have the measure, congruent when I don't have it. The perimeter is in the same ratio of as the sides. So the perimeter of the small triangle is going to be 1/4 of the perimeter of the big triangle because the ratio of the sides is equal to the ratio of the perimeters. The large triangle is going to have a perimeter of 4 times the smaller one. So this is going to be 4. And then the areas, you square the ratio of the sides. So for these, the ratio of the areas is equal to the ratio of the sides squared. So that means instead of 1:4, it's going to be square 1, square 4, it'll be 1/16. So the area of the large, or of the small triangle is 1/16 the area of the small one, or of the big one, and then vice versa. So to get from, if you want to get the area of the big triangle, you would actually have to multiply the small triangle's area by 16 because you have to square the ratio of the sides. So that's where I'm coming up with it. So I'm coming up with this because I squared 1/4. So I got 1 squared over 4 squared, so you get 1/16. And this I got by just squaring 4. So that's it. So knowing those properties, drawing a picture is going to be important. Also, you should be able to construct this if it was a construction. And it's really easy. It's just measuring with your compass the arcs and continuing it.